بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so today we're going to start chapter number 4, which is about NumPy and also an overview about linear algebra. I can say this is one of the most important lecture in this course. And I've done a little bit more effort in this course to link 3 different topics. So usually when we teach NumPy from Python programming perspective. This is how it works and so on. In this lecture, because I tried to map between NumPy and the concepts of linear algebra and also illustrate how this will be needed later on in deep learning, in AI, and machine learning applications. So I'm going to introduce the NumPy concepts and link them to linear algebra. So it's going to review for those who already took linear algebra and an introduction for those who are new. But most of you have already taken linear algebra concept even in higher school. So these are like common concepts. And also how to use NumPy data structure in order to represent a vector, in order to represent matrices or matrix operation, and why do we need to use linear algebra in AI and data science. So this is basically very important, and it correlates to several use cases in AI and data science. So let's get started. So NumPy, like pandas, it's a third-party library. It's a fundamental Python library for numerical computing and provides support for large multi-dimensional arrays and matrices. It includes a collection of mathematical functions to operate with this array. So you can create an array. This is an example of one-dimensional vector of 5 elements. And we usually use NumPy, so we need to install NumPy in the beginning. And we can denote it as MP. And later on, you can create an array. And an array, it can be one vector, one-dimensional vector, or multi-dimensional matrices. And the array will have a type, for example, int64. And why we use NumPy? It's because of its high efficiency, especially in large data computing. So it's implemented in C, it provides fast execution, and contains a lot of library for linear algebra, for Fourier transform, matrix multiplications, which are made in a very fast fashion. So it's basically also integrated in several scientific computing libraries like PyTorch, also TensorFlow from Google, which are sophisticated libraries for machine learning and deep learning use cases. So why do we use NumPy? It's optimized for numerical operation with n-dimensional array support. So you remember when I introduced lists, I made an example, the difference between list and NumPy array, and you can observe the huge difference in terms of computing. And now, when you deal with a huge amount of data and very large models, you need to optimize the computing as much as possible. Otherwise, you will not be able to train large models, and you cannot make very good prediction. You cannot also take benefit of your data. And this is why NumPy was built for this particular purpose. Okay, so it's an essential computing for scientific computing with Python. It facilitates complex mathematical functions and operations. Yes? Yeah, so this vector is one-dimensional. It has only one axis. A two-dimensional matrix, it has 2 axes, rows and columns. You can have 3-dimensional, you can have 4-dimensional, you can have n-dimensional, up to 100, even more. Like now, for example, deep neural network, they use very high dimensions of matrices, okay, to represent the different layers of a neural network. So installing NumPy, you can use pip install with Python package installer or conda install if you use conda distribution. And you can also verify the version of NumPy arrays from one version to another. It may cause compatibility issues with some codes. Okay, so we can represent scalar. NumPy is for multi-dimensional array, and it can also represent scalars as like arrays as well. So a scalar is a single numerical value that can represent qualities. So it's just a variable like an integer or a double, but we can represent it as a NumPy array. And this is usually we do it for compatibility issues. Later on, you can make the sum of different type of arrays with different dimensions. So this represents a scalar, okay, and is encoded as a NumPy array, np.array 5. It's a scalar in NumPy. And later on, you can add, subtract, or multiply with other integer variables. This is possible. Okay, so the type of X is NumPy array, and this type here is actually an int variable. And Y will be also a NumPy array. So there is a very important concept that is called vectorization I'm going to introduce at some point in time later in this course, which allows an array to be added to be multiplied by a number or by a simple variable. Okay, so what is the difference between lists and NumPy array? So the lists are flexible, but they are slow for large data set. If you have a very huge amount of data set, it's not common to use lists. On the other hand, the arrays are optimized for speed and designed for high performance numerical operation. So this is an example here on how to create one-dimensional array, okay, by converting or casting a list to a NumPy array. So you can have a list, and later on, if you want to use this list for high performance computing, you can convert it into NumPy array. So the constructor of a NumPy array can take a list as argument and is going to convert it. And also it can take two lists as a matrix. So this is going to convert these two lists between brackets. You can see there is outer brackets here and the brackets for the two lists. This is going to be converted into a two-dimensional matrix as a NumPy array. And you can use .shape, dtype, so we will see these different functions later on. So
ستحتاج إلى فتح قفل الآيفون أولاً.
Look at this code. Here we create a one-dimensional matrix, and here we create a two-dimensional matrix. And in order to see the different characteristics or properties, so we can actually display the shape of an array. So what is the shape? It tells you how many elements, for example, number of rows, number of columns in case of a two-dimensional array. So the shape of a two-dimensional array will be the number of rows. First, we have 2 rows here and 3 columns. So this is the first row, this is the second row. Okay, so .shape can capture the shape of a particular array. And here we have one-dimensional array with only 5 elements. We can also investigate the type of the data that is being stored. Of course, here the data type will be inferred because Python is not a typed language. So the type is dynamically casted based on the values assigned. Since I have assigned integer values, so the type of the NumPy array will be int64, which is the default int values. And the dimension, okay, it tells you what is the dimension of the array. As already mentioned, NumPy arrays is for multi-dimensional arrays. And the dimension can be 1 if you have a vector, 2 if you have a matrix, 3 if you have a 3-dimensional array, and 4 and can be larger. Yes?
Do you see that the array is a list of lists in a set?
Okay, it depends what do you mean a list of lists in a set. It's not. It's another structure. You know, you had it's a different structure which is encoded in the memory in a different way. You had a course on data structure, and you have the concept of the pointers, which shows the relation between the different elements. So NumPy array is implemented in that way, okay, such that it optimizes the computing performance. Okay, yes. So there is an internal pointer structure for the NumPy array that makes it high performance. Okay. Okay, so ndim is to return the dimension, dtype to return the type, and shape to return the shape. And the type is very important in high performance computing because if, for example, you work with float 64 or float 32, this is going to give you a high precision, but is going to impact on the speed of execution. If you make multiplications of a large amount of numbers with high precision, it's going to be much slower. So sometimes we can change or downgrade the precision of the type either for integer if we don't want to have a very large range of these integers, or for float numbers in order to optimize the speed of execution for these arrays. Okay, so let's talk about one-dimensional vector right now. So in linear algebra, a one-dimensional vector is basically a sequence of values which we represent as such, v1 until vm. This is the mathematical representation. Okay, it's a collection of n elements into one dimension. We have one axis. Sometimes we say it's one axis, one dimension, or one channel. These are different terminologies that we use in AI and data science. And here it has a couple of elements. Let's take the simplest case of representing a vector into a two-dimensional space. So the vector will be expressed by two coordinates, x and y, and this is the vector representation, right? From 0 to the coordinate over here. And we can do the same thing also in three-dimensional space, like here. So this is a vector, x equal to 3, y equal to 4, and z equal to 5. So this is the vector representation, and we can use NumPy array to express these vectors. For example, this vector, we can write it vector 2D np.array 3, 4. So this is going to create the following vector. And this one, 3, 4, 5, is going to create a vector in three-dimensional space. Of course, it can go to higher dimensions, but we cannot visually represent it more than 3 dimensions, as you already know. So what is the usage of vectors in data science? We use them usually to represent the features, خصائص البيانات, the features of the data. So any kind of raw data is usually converted as features. Like for example, an image by itself is just a two-dimensional array. Or could be, if it is grayscale image, we have two-dimensional array with different gray colors from 0 to 255. That's an example. In also natural language processing, we use a vector to represent a particular word. Every word is represented as a vector. So there are different use cases of using vectors in data science. And this is how we do operations. So we can make the sum of two vectors. Mathematically, the sum of two vectors. You're going to take a vector v and w, and you will sum the elements one by one. So v plus w is going to result 2 plus 1 is equal to 3, 4 plus 0 is equal to 4, and 6 plus 1 is equal to 7. We can do the same for subtraction also, and you can also multiply by a constant or by a scalar value. Okay, so here in this case, this scalar value is going to be applied to all the different elements, and this is the resulting point. And this is how we implement this in Python. We define v and w, so we can make the addition, v plus w, the subtraction, and you can see here, you can apply directly the operation on the vectors. You don't need to make a for loop and make the implement. There is already algorithms, okay, that were implemented in the background by the NumPy library in order to do this execution in the background and quite fast. Now, if you want to do that in the same way using a for loop, is going to take much longer. For loop is the worst case that you can have for high performance computing. And while we're going to learn about vectorization, I'm going to make you demos about this. Okay? And you can also multiply by a vector, and you can see here, so this is the vector w, this is the vector v, so this is the sum of the two vectors, and this is the subtraction of the two, v minus w. And you can see this vector is basically going from this point to this point exactly. Okay, it's v minus w, so it's going to give this vector over here. And this is if we multiply by a negative value, we're going to have the opposite direction of w. Yeah, so this is just the same example showing the different operation, the sum, subtraction, and multiplication by a scalar. And this is a similar example in two-dimensional. Okay, so we have the vector w, we have the vector v. This is the sum, this is the difference, and this is multiplied by a negative scalar value. Any question?
What is secret?
See, it's a scalar. It's just a variable, okay, that we multiply by number. Okay, now applications of vectors or NumPy arrays in AI. In the context of computer vision, for example, this is a picture of a cat, and this is when we load the picture, we can load the picture of a cat into a NumPy array. Okay, so I don't have the code here, but you know what you see here, what is 255? It represents what? White. The white color. Look, so these first elements here represent the top, okay, the pixel in the top and in the left corner. Okay, so you can see we have a lot of white here. This is why all the values from the top and also from the bottom are all 255. And here we have 3 channels, red, green, and blue channels. This is why we have, for every pixel, we have 3 values. Okay? So in computer vision, images are vectors or matrices of pixels. Okay, and this is a simple example of 2 by 2 pixels. Okay, I can create a pixel of, this is black, this is white, and this is black. So we use also vectors, NumPy arrays in natural language processing. So, and this is used for word representation. So the words in NLP are represented as vectors in a high dimensional space. And this is what we call it as the word embedding. So the word embedding is basically a vector that represents a certain word or a certain token in the language of large language models. And this embedding vector can be of different size. So usually we take it 128 or 256, 512, 124. So it's basically an exponent of 2. Okay? It can be anything, but you know, the rule of thumb, it's an exponent of 2, starting from 64, 128 to 56, 1024, 2048. These are actually the common embedding size of a word in multidimensional space. And these vectors, they usually capture, you know, we don't make them as a random vector. And you will see the beauty of mathematics later on how to represent the similarity between words using vectorization. So these vectors usually are built in a way to capture the semantic meaning between the different words. And look at this example here. Of course, this is just a fake example. So I can represent the word apple using a NumPy array with these numbers. And banana with another NumPy array, and cherry. Of course, now this is a fake example. It's not really representative of the meaning of the words. But just to show you that we can make functions or mapping in a dictionary between a word and its corresponding embedding. And you can retrieve the embedding of a word, you know, by using the word as a key. But let's look at this example now, which is more realistic. So in machine learning, later on when you do machine learning, you can train some models so that they create word representation such that the words that are close to each other, these vectors will be also close to each other. For example, we can see here we have apple, banana, all of them are fruits. So in principle, they should be close with each other. Okay, I'm going to show you the similarity later on, but you know, this represents a real representation of the word apple by using this trained model, embedding model, okay, which is called English Core Web Small. Small is because it's a small of size. It has a small size, so each word is represented in 96 values, an embedding of size 96 elements. Of course, there are other embedding models that are larger. I'm going to show you some others. So, and here we use the library SPACY, Spacey. Okay, Spacey library, it has models that represent word embedding. It's not the most sophisticated, but these are just some educational examples. Yes? Yeah, just now the purpose of this slide is to show you that in machine learning, we use NumPy array to represent images and also to represent words. Because now if you are learning this, you must understand why I am learning this.
And the vector on the right, how did they compute?
This one? So this one is, we call it an embedding for the word apple. So this embedding is not just random numbers. They are constructed in a way to capture the similarity between the words. But now all of you are saying, how can I capture the similarity? How can I know that two words or two embedding are similar and they represent similar words? Of course, I'm going to show you right now with the dot product. So the dot product, this is one of the most fascinating concepts in linear algebra. And basically has the meaning of capturing the similarity to some extent between two different words. But let's look at the mathematical definition of what is a dot product. The dot product basically of two vectors, x and w, and usually now in machine learning, x represents a feature of something and w will represent a weight. We do linear transformation. Okay, and it's basically the sum of xi, wi. Take two vectors, vector x, 2, 4, 6, and vector w, 1, 0, 1. If you make the dot product, you're going to make the sum of the product of each element. I will multiply this element with this element plus this element multiplied by this element plus this element. So it's kind of correlation, let's say, from probabilistic perspective, but it's not really correlation here. Okay, So this is how it looks like. You have a vector x, you have a vector y. Of course, they should be compatible. You cannot do dot product on non-compatible vectors. The number of rows or the number of columns must be equal to the number of rows. And you will make element by element. Look, x1, y1 plus x2, y2 plus x3, y3. So the result will be a scalar. And this scalar will be a value that captures how close these vectors are. If it is high, it means they are close to each other. If it is small, if I find 0, they are completely different.
So when you say close, what do you mean?
So two vectors, I'm going to show you. I will illustrate this. Okay, but for now, let's understand the definition, how we calculate it. And you know, in NumPy, we use np dot. We provide the two vectors must be compatible, otherwise it's going to make an exception. And for example, multiplying this vector by this vector, we're going to find -2, same as we did here in the calculation. Okay, so what does it mean, dot product and similarity? Let's look at these plots. Here I have two vectors that are equal, exactly the same. The dot product is equal to. Look at these two vectors. This vector is orthogonal to this one. If you calculate the dot product, 0. They are completely orthogonal, so no relationship here. I keep always this one because identity is the strongest correlation between vectors. And look now, these are also they are not equal, but they have the same direction but different amplitudes or magnitudes. Okay, so the dot product is 1, is half of this. Okay, so there is similarity, okay, but still the magnitude of this one is smaller than the other one. But the similarity is not the same, but of course it's much higher than this one. So what really counts for the similarity is the orientation and the magnitude of the vector. If they are completely equal, they will have the same magnitude and the same orientation. So the problem here was the orientation is different. The angle is 90 degrees. And you know that the sine of 90 degrees is 0. Okay? And this is later on I'm going to introduce what we call cosine similarity. So it has something to do with also trigonometry, the sine and the cosine. The sine of 90 degrees is 0.
What's sine? What's the correlation between sine?
Yeah, let's look at the angle here. Okay? The sine, it tells you...
That's the
Yes.
The matrix.
Yes.
And is dot product
Yeah,
always constant?
let me complete the illustration. You'll understand just a moment. So look now, we have these two vectors with smaller magnitude and a little bit of deviation. We find 1.5. Okay, so now we can understand that the dot product, it has something to do with how close the vectors are, at least visually. Okay, so this is what I want you, this is one of the main concepts of the transformer technology, what we call the self-attention mechanism. It's based on the dot product between two quantities. And this dot product calculates the similarity between your prompt and what it has to generate. You see? So these foundational things, you will find them everywhere later on when you deal with machine learning and deep learning courses. And look at these ones. They are completely the opposite. It's not 0, but it's even negative sign. Okay, so here we have 180 degrees, the angle between the two vectors. Okay, any question before I move? Yeah.
The numbers
Hmm?
depending on what the numbers inside the vector.
Which numbers? These are the coordinates. This is 1, 1.
Like when you want to see apple and banana, the similarity
Forget about it.
is not
Forget about it. Now, understand the dot product gives you similarity between vector representations. Forget about it. I'm going to introduce that, but forget about it. Yes?
And third, dot product calculation does always produce a single digit from -2 to 2.
No, from negative, from negative values to positive, it can be positive or negative. It can be infinity, depending on the scale of the vector.
So if it was three-dimensional, and two vectors were identical, would it be 3?
No, it's based on the calculation. I cannot you will be 3 or 4. It's based on the numbers, on the coordinates. There is no, these values are just the result of a calculation. They are not fixed values. It's not -1 or 2 or 1.5. This is very typical example. Okay, now we understand that the dot product gives some intuitions about the similarity between vectors, at least you know in graphical representation. Now let's look at this one. I'm going to use another embedding model which is called Core Web. So this is the medium scale. And I'm going to take three words, apple, banana, and lion. And then I'm going to find the embedding of each word. And look now, I would like to calculate the dot product between apple and banana and apple and lion. And you can see the result here. So this embedding model doesn't contain random numbers about the words. But this word or this vector were built such that they can capture some relationships between the different words. It's a very complex process, but at the end is going to converge to a distribution when words that have some kind of semantic similarity will be close to each other. What does it mean close to each other? It means the dot product will be large. And the words that are far from each other, the dot product will be smaller to some extent. Okay, and we can observe this visually right now. 911 and the difference between apple and lion is 1. So here it's 161. It's smaller, the dot product. So we can understand that this is not bad embedding model because the relationship between apple and lion is, of course, naturally smaller than the relationship between an apple and banana. These are fruits and these are of different types. Yes?
Can't we represent the similarity between 0 to 1? Because when it's
We will come to it. Don't jump. Okay? Because that product is not normalized. Now we talk about normalization. That's the next topic. Let's look at this one now. I used the small embedding model, SM. Still we have differences. So the dot product between apple and banana is higher, but you know the difference is smaller. So we can understand that when the embedding model is larger, it can capture more nuances between the different words. This is why, to have better accuracy, we try to use larger embedding vectors. But of course, this is going to have an implication about the speed of execution, the memory requirement, and so on. So there is always a balance to do between the accuracy and also the execution of processing and the memory requirement. So you can understand now why you are learning NumPy. You know, NumPy is the core technology of every scientific computing and AI data science. Okay, I want to bring you these models because this is what you're going to see in the future. You'll do AI, deep learning, you know, it's all based on these very important concepts. But as you already mentioned, these are numbers that are not normalized. We don't know what is the range of these numbers. And this is kind of annoying, you know, it depends on the model. I want to have something, you know, regardless of the model, is going to give me a value between 0 and a probability of similarity level. And this is why we need to have normalization. You know, these vectors can take any value in space. Especially imagine you have a high dimensional vector. When you multiply with them dot product, you cannot expect what would happen. You can have very large numbers. This is what we call exploding values. Or you can have very small numbers, vanishing values. We don't want to have this. So usually what we do, we try to normalize. And there are different ways of normalization. So we take the vector and we define all its values. So one of the ways is to define by the norm. The norm of the vector is the square root of the sum of the square of the values. Okay? So this is going to give a large number, larger from any other number. And dividing by this value, you're going always to have a normalized representation. There are other type of normalization, dividing by the max of all numbers. You know, there are different type of normalization, but this is what we call the L2 normalization. Okay, L2 normalization. We divide by the norm of the vector. And this is an example here. So vector v3, 4. We calculate the norm. Square root of the sum of the squares equal to 5. Divide 3 by 5, 4 by 5, and now I have a normalized vector, 0.6, 0.8. Values between 0 and 1. And this is excellent because it will make a huge advantage for the numerical stability. When you multiply values between 0 and 1, you're not going to have exploding values. Okay? So pretty much normalization is a standard in training machine learning models. We usually take a data set. First of all, we normalize all the data. Why? This is what we call to make sure the numerical stability of the model when we train it. So how to do that? Normalization, we use np.linealg. So linealg, it's linear algebra. It's a library for linear algebra. .norm, and you put the vector, is going to provide you the norm of V. If you want to create the normalized vector, you take V, you divide by the norm of V. So this is V in red color, original vector, and the normalized vector is represented in blue color. Bismillah ar-Rahman ar-Rahim, wassalatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Okay, so this is the continuation of the previous lecture where we have introduced NumPy arrays with the concept of linear algebra. And we have learned a lot of things like vectors and also the dot product and how do you use vector in AI data science in context of computer vision or natural language processing. And the last thing we've talked about is the dot product. And what was the benefit of the dot product? What does it do? Yes?
Helps us get the similarities between embeddings.
Between embeddings is one of the use cases, yes?
Basically show the similarity between group of words, for example, banana and apple and
Yeah.
banana and lime.
Yeah, so it can show some kind of, let's say, similarity between vectors. You know, everything in AI and data science are vectors. Everything. Any kind of data is going to convert it to vectors, representation, and then we will put all these vectors together so they will represent multidimensional matrices. Yes?
Show the orthogonality between vectors.
Yes, show the orthogonality, which means they are completely different, or they can be also the opposite. So this is the calculation on how to do it. Okay, it's basically the sum of the product of the values of the vectors. This is the expanded version. And we have observed through a simple example on two-dimensional space, okay, the relation between the dot product and how close the vectors are. And you can see where they are completely the same. So we have a high dot product. If they are orthogonal, the dot product will becomes 0. So this shows an example about measuring kind of similarity. It's not exactly the similarity, okay, because it's going to give a number which can be large or small, but of course the magnitude of this number is going to give us a degree of similarity, let's say, okay, how close these two vectors are. And here we have multiplied the vector just by 0.5, so we have still similarity here, but it's less because now they have the same angle, but they don't have the same magnitude. So the similarity is based on two metrics: the angle between the two vectors and also the amplitude or the magnitude of the vector. So we can see now we have a smaller magnitude and also some kind of vector deviation in terms of angle, and we have a smaller dot product between these two vectors. And while they are completely the opposite, so the dot product will be negative. And then we took a more realistic scenario where we have used word embedding. So we've used an embedding system, which is the medium one, okay, that can convert every word to a particular embedding vector. And these embedding vectors are not completely random because they are built using machine learning to capture a certain type of semantic or similarity in the meaning between the different words, such that if the words are close to each other, the dot product of this vector will be close or will be large, sorry. And if they are not close to each other from meaning perspective, they will be smaller. So basically, this similarity is based on what we call a vocabulary. So when the vocabulary is very large, we need to have larger embeddings. So usually we're going to take a certain number of words and then calculate an embedding vector based on a vocabulary. If we change the vocabulary, this embedding will also be changing. Of course, you will learn later on in machine learning and deep learning, in natural language processing, in this track, how we can construct and build this type of embedding system. And what we observe here is that when we calculate the dot product between, for example, apple and banana, we're going to find a large number because they are semantically close. And between apple and lion, we will find a smaller number. And these numbers, basically, they depend on the embedding type. So the MD has a size, I think, of 512 or probably less. And we have also the small embedding, which has an embedding shape of a vector of 96 elements. So here we still find that apple and banana has a higher dot product, but the difference is much smaller than in the case of this embedding. So usually when we increase the embedding size of a vector, we're going to have more capabilities to differentiate between the words. We have more space where we can organize our vector in that space, because the space is multidimensional. Imagine that you have only three-dimensional vectors. You don't have enough freedom to move into only in 3 axes. But usually we're going to use 96, 300 dimension or even more to have more space to represent these vectors and similarities.
Do we usually use the same model for code our program, or do we do?
No, there are plenty of models, maybe thousands of models. And every model has pros and cons in certain contexts, depending on what accuracy you want to have, what is the speed of execution. You know, there are multiple factors on which model to use. And you can build your own model. Imagine that you want to build a language model, and you have a certain vocabulary that you have collected from the internet, and you want to have something very specific. And now, for example, if you go to OpenAI, they have their embedding model also. It's multilingual, can work for English, can work for Arabic. There are other embedding model only for a particular language, for French, for example, for English, for Arabic. So you can build your embedding model depending on the objective. So that model, as we can understand from the name, it comes from the web. So people actually will scrub the web, collect a lot of data, and then use this information in order to build these embedding models. So now, what do we observe? We cannot say here very clearly, the extent of similarity between the vectors, because it's going to give a number which can be very high or can be small. So how can I compare between the dot products in this case or in this case? I don't know what's even the scaling. Okay, so in order to improve the accuracy of the similarity, we actually use normalization. And normalization is one of the most important aspects when we train machine learning models. Because usually, and as already mentioned to you, everything in machine learning and deep learning is basically we create vectors, matrices, and we do dot products or matrix operations. And imagine that you have large numbers and you do a lot of dot products or multiplications or summations. You will end up probably by having very large values that will go infinite. Or you can have very small values, go to minus infinite or even to zeros, and these zeros at the end, if you multiply 0 by something, it's going to result in 0. So it's going to compromise all your sequence of operations later on. This is what we call exploding values or vanishing values. We don't want to be into this kind of situation. So usually when we do multiplications, we try to normalize. We're going to have values up and down. So what we will do, we try to put all these values between 0 and 1. And this also actually happens in every type of operation. After we finish certain type of operation, we will normalize again and again and again. And there are different ways on how to do normalization. So one of the ways is to use the Euclidean distance, okay, of the vector. You know, what is the Euclidean distance? Is the distance between 2 points. Okay, so we calculate the distance, the Euclidean distance, which is called the L2 normalization, and we divide by the value of the vectors, of the elements of the vector. So imagine that you have a vector v. What do? We calculate the norm. And the norm is nothing but the Euclidean distance. And you have already done this maybe in two-dimensional space. You have 2 points, and you calculate the Euclidean distance, the square root of the sum of the squares. Okay, and this is just generalized to n dimensions. You have a vector of n dimensions. And then it turns out that when you divide all the elements by the Euclidean distance, or by the norm of the vector, the L2 norm of the vector, you're going to have values between 0 and 1. So we're going to convert a vector into a normalized vector, because the norm of the normalized vector is equal to what? Yes?
The vector divided by the Euclidean.
Yeah, I know. The norm is equal to what? So it's equal to 1. Okay, because we're dividing by the norm. Okay, so this vector has a norm, and we divide by the norm, you're going to find the norm of this vector is 1. And this has very important characteristic to make all type of computation stable.
It's always 1?
Yeah, because it's a normalized vector. So a normalized vector, by definition, its norm is equal to 1. Look, it's a unit vector. We call it a unit vector, or a vector with unit length. It means that its norm is equal to 1. Is it clear?
Yes.
Okay, now what's the benefit? Instead of comparing vectors like this, we're going to compare normalized vectors. Okay, so now even the magnitude and normalization is not going to affect the direction. It's going to affect the magnitude, but it's going to maintain the proportionality of the magnitudes. Okay, because we're going to divide by the same value, which is the norm. So you have this vector, 2 vectors, they're going to be normalized. The proportion of the magnitude will be the same, because we're dividing by the norm. واضح? We divide by a constant, so it's proportional. And this is an example, if you didn't take linear algebra, linear algebra is fascinating, and it's basically the pillar of AI and data science. Look, if you have a vector 3, 4, I want to normalize it. I calculate the norm, okay, the Euclidean distance, and then divide 3 by 5, divide 4 by 5, and finally I will find 0.6 for the x value and 0.8 for the y value. And this is the representation. You start from 3, 4, and you get a normalized vector whose value, okay, is the norm is equal to 1. Okay. And this is the NumPy, how we do it. So NP array 3, 4, we calculate the norm. And to calculate the normalized vector, we just divide V by the norm. Another way to do normalization is called L1 normalization. Instead of calculating the Euclidean distance, we calculate the Manhattan distance. So what is Manhattan distance? We're going to calculate the sum of all the absolute values of x. So this is going to give the a positive value, which is the Manhattan distance. So Manhattan distance, imagine that you have a point here and a point here. So the Euclidean distance is basically the straight line between the 2 points. The Manhattan distance, it goes actually in this way. Okay, so it's going to count either going left or right or top or down in order to reach. So this is the Manhattan distance. It's the sum of x to reach the next point. The sum of all the values in positive, because it's going to be incremental. Now, for example, what is going from here to here, for example, to this point? Okay, now this is the Euclidean distance. If I want to calculate the Manhattan distance, it's going to be 0.5 plus 1, 2.5. Imagine that I have a point that is down below. It's going to be 1.5 plus 1, because I take the absolute value, even if it is in the bottom. So the distance is the same. The distance is a positive quantity. Okay, so whatever, for example, the point is on the top or on the bottom, the Manhattan distance will be the same. And this positive quantity, when you divide by all the values of the x vector, is going to provide you values between 0 and 1. And this is another way of normalization. The most common way of normalization is L2 normalization, but L1 has also some advantages in some situations. Yeah, this is L2 normalization. It's based on the Euclidean distance. Okay? And this is L1 normalization. Okay. So normalization in computer vision, yes?
For the L1 normalization, when you add the x, how do you get 0.6?
No, I didn't make. No, this is for L2. It's not this. Just a moment. No, this is, yeah. This is for L1. This is for L1. Look, now it's 0604, and in L2 it was 0608. Okay.
So the other one?
Yeah, it's okay.
First one is,
No.
For L1.
Yeah, this is L1.
Yes, these results are for L1.
Yeah.
So how do you get 0.6?
If you make, I didn't put the calculation here. If you put numerical calculations.
Okay, what
3, we have 3, 2 here. This is 3.
3, 2, so 3 plus 2, is that how you get the
No,
L1 normalization?
we calculate this quantity.
And what's the x?
It's 3 plus 2 here, yes.
3 plus 2 is 5.
If you divide 3 by 5, you find 0.6. And if you divide 2 by 5, you find 0.4. Yes, we will divide by this quantity. Okay, so it's the sum of the coordinates. Okay, the sum of the coordinates.
L1.
This is L1.
L2
Euclidean distance. This is L2. The sum of the square root of the sum of the squares.
If I use the same vector, two different normalizations, will I get the same answer?
No. Like, and from statistical perspective, they may converge. Usually which normalization to use, there is no wrong and correct answers in machine learning. So usually we try. It's called hyperparameter. It's something you try and you see what will be the impact on the result. Okay? Yes?
The square, the root won't cancel out with the square and it will be the same thing? Or?
Yeah, yes, no, same thing. This is compact, this is expanded representation. Now, we use normalization in computer vision. So usually in computer vision, we have pixels between 0 and 255. And you can imagine now, if you do computation at that scale, it's not going to converge. I have one of my videos showing if we train a machine learning model neural network on non-normalized images, it will not converge. So I got, it was a very simple example. You got an accuracy about maybe 30%, kind of random, 30%, 40%. You just normalize, you run the same algorithm, you're going to have 70% of accuracy. So normalization plays an important role in the stability and the convergence of machine learning models. And here, so the normalization is divided by the L2 norm, which is the Euclidean distance. Okay, sometimes there is called, we divide by the maximum value, so we can normalize the pixels because the maximum value of the pixels is 255. So if I divide all the pixels by 255, we can also get values between 0 and 1. That's another normalization way that we can do. And you can see this is the original image in grayscale, and this is the normalized image. You don't see any difference. Okay, so actually, Matplotlib and image reader, usually they are able to read the pixels whether normalized or not normalized. Yes?
When you say the vectors for the picture, it's each row of pixels.
Yes.
The value is a vector.
Yes.
Is the array for the.
Yes. Each value
So
is a
it's
pixel.
basically doing row by row, and each row has the set for each pixel as an element of the array.
Yes. And now this is the printing the image vector, and this is the normalized image vector, are values between 0 and 1. Okay. In natural language processing, also we can do normalization. So here we do normalization to, okay. In this slide, I only show how to calculate normalization. So how do we use it? It's for calculating the similarity. The similarity, instead of comparing the dot product of the vectors, the embedding vector, we calculate the dot product of the normalized embedding vectors. So look now, here we calculate the embeddings, and then for every item, for every vector, we calculate the norm of the vector. Okay, so the norm of the apple is 43, 31, and 55. So we're going to use this norm to divide, okay, the embedding vector by its norm. And look now. So this is the original L2 norm, which is 43. The normalized L2 norm for apple after normalization. So this is the norm of the normalized vector. As I told you, the normalized vector, it has a norm equal to 1. Okay, so here we calculate the embedding. We calculate the normalized vector divided by the norm, which is equal here to the normalized vector. And finally, you can find the norm of the vector, which is 43. The norm of the normalized vector is 1.0. And this is the normalized vector, okay, itself. There are values between 0 and 1. Not only that, its norm is equal to 1. And based on this, when we do the normalization of vectors in embedding, we can calculate a more accurate similarity, which we call the cosine similarity. So the cosine similarity, it's basically the dot product of the two vectors divided by the norms. And basically it's the normalized vector x dot product with the normalized vector y. Okay, so you can consider as x divided by its norm and y divided by its norm. So it's basically the dot product of the normalized vector. This is what we call cosine similarity. And it's because it's kind of an estimation of the cosine between the two vectors. You know, the cosine, it's a value between 0 and 1. So it's basically represent the cosine, the angle between the two vectors. Because when these vectors are normalized, okay, if they are equal, they should have the same magnitude. Okay, so since we have normalized all of them, and the norm is equal to 1, so all the similarity, we're not going to consider the magnitude for the similarity, but we are going to consider the divergence with the angle. Okay, because now they are normalized. This has a norm of 1, and this has a norm of 1. So the cosine between the two vectors represent the amount of deviation. And when we have a lot of deviation, what does it mean? Perpendicular. What is the cosine of 90 degrees? 0. The cosine? The cosine of 90.
Yeah, it's 1.
It's 1, yes. The cosine of 90 degrees is 1. The sine of 0 0. No, the cosine is the cosine of 0 is 1, and the cosine of 90 degrees is 0. Okay, and that makes sense because when we have orthogonal vectors, the cosine it's 90 degrees, so the cosine is 0. Orthogonal vectors will have a 0 similarity, cosine similarity. This is what we call it cosine, because the cosine will measure the similarity between the angles of the vectors. Does it make sense? Okay, and when the vectors are colliding, so the cosine will be equal to 1. Voilà. So you can see now, starting from a word, you can convert it to an embedding, and this embedding can be normalized, and then I can assess how close. And this is the when, for example, you search in Google, you type a certain keyword, we're going to convert your question into an embedding vector, and then all the text that is in the web is vectorized. And you are going to make the cosine similarity between your question and all the information available, and we will bring you the documents that are the closest to your question. Okay? So this is one of what we call semantic search. We search the web or we search documents based on the semantics. There are other search techniques, but this is now very popular, especially with large language models. I don't know if you have heard about retrieval augmented generation. So you know that, for example, ChatGPT or large language models, they might have hallucinations. You can ask a question and they don't provide you with the right answer. Maybe it was not trained in this particular topic and so on. So what now people do, when you ask a question, for example, you ask a question about, you remember the chatbot that we have done it last year. We had a chatbot here. So this chatbot had hallucinations. So what we did, we brought a lot of documents from Prince Sultan University, policies and student guidelines and so on. And now when everyone or anyone asks any question, we're going to take this question and make semantic search on all the documents. You want, for example, I want to drop a course. So I'm going to look for all the documents, and some of the documents will have policies for dropping a course. So we're going to bring several documents that are related to this question, provide them to the large language model. It will understand now what is the context of the question and what is the possible answer, and then we use the large language model to generate answers based on this. So you can see these simple tricks are being used now in sophisticated systems like a large language model, retrieval augmented generation, to look for documents that are relevant to your query and then provide them much better response. So it's basically based on this. You know, the transformer technology, which is based on the self-attention module, it's basically an application of the cosine similarity, okay, to look for particular information that is relevant to an input. Any question? Yeah.
The cosine similarity is basically doing the normalized for a vector and normalized with the other than that model.
Yeah, so we normalize every vector, and then we calculate the dot product of the normalized vectors. And this is going to give you the angle, okay, the cosine of the angle. Okay, so if these vectors are close to each other, the cosine is going to be close to 1. So they are strong, they have strong relation, semantically close, if we are in NLP. And we do this not only in NLP. For example, how to do face recognition. So usually we take a picture of the face and we convert it to an embedding. So there are algorithms that are trained such that if two pictures are of the same person, their dot product or the cosine similarity will be close. So when we take your picture, we're going to compare your picture with a database of faces, okay, an embedding of these faces. And then we will extract the embedding that is closest to your new picture. Because when we train very well these models, your face will have kind of a fingerprint. Not exactly the same, but every time is going to generate an embedding that is close to yours. Okay? And there are techniques like CME's network to train models like these images are the same or these images are different, and based on this is going to update the weight of the model to create correct embedding for these images. So you can see now, you are studying, I want just to illustrate all these examples to understand why you are studying NumPy, why linear algebra is important, is because we can use mathematics to solve problems easily. Okay? So all these syntax or formulations, you can find them anywhere, but the most important thing is your ability to use them whenever appropriate, to build models, to create architectures, to understand existing models. Okay, this is very important. Okay, so that's a simple problem here where I provide you two vectors, we calculate the dot product, we calculate the norm, and this is how we calculate the cosine similarity between both. And look now, this is called the heat map. And the heat map usually it shows the correlation between elements on the x-axis. So now this heat map is for showing the correlation in terms of similarity, semantic similarity between the words. So of course the diagonal is 1. Every word coincides with itself. So the cosine similarity is always equal to 1. And now we're going to calculate the cosine similarity between, for example, this is apple, and this is how it relates to leopard, tiger, lion, fruit, banana, and apple itself. And this gives a lot of sense. Look now. If it is red, it means it has high similarity, high correlation. So the word apple is correlated to banana to 66%, of course, based on this embedding model. This is a large embedding model. And 67% with fruit, but not correlated with lion, tiger, and leopard. So this is a visual representation of the semantic similarity or the cosine similarity between word embeddings. Okay, so you can apply the same thing. You can see now we have a square here that is red and another square between animals, lion, tiger, and leopard. So the tiger and leopard are highly correlated and a little bit less between the leopard and the lion. It makes a lot of sense, right? So you can see now how these techniques can be used for retrieval, for semantic search of information into large amount of documents. Any questions? Okay. And look now, if I don't, this is the same correlation without normalization. There is no ground to tell about the magnitude, you know. So the magnitude here is not going to give me clear semantic similarity between the different words. So now, what is the main lesson? Normalization is an important process in AI, data science, and machine learning, okay, to have statistical stability of the operation that we want to achieve. Here, our operation is semantic similarity. There are several other operations like training neural network models or training machine learning models. Okay, so this is a very important concept about normalization. And now, the same thing like we did with vectors. So here I'm going to make an overview about matrices, which are n-dimensional vectors. And matrices can have multiple dimensions. We already talked about 2-dimensional or 3-dimensional, but this is just a generalization. So you can do the sum and subtraction. Of course, the sum, it's element-wise sum of the matrices. And also the same thing for the subtraction. You can multiply a scalar by a matrix. And this is possible in Python. Look, in Python, we can make the sum of 2 matrices. Now, I think in Java, you have to develop a for loop to do that. This is called vectorization. Inshallah, next lecture, I'm going to have a clear overview about vectorization. And it means that there are already algorithms that are very high speed that are able to do all the computation on the behalf using like performant data structures. Okay, you can also multiply a scalar by a matrix. So you should never ever think about using a for loop to do matrix operation. You need to leverage the vectorization capabilities of Python and NumPy arrays to speed up the operation.
A for loop would make the code.
That's the worst thing that you can do, yes. For high performance computing is to use for loops. Usually we avoid doing that, yes, unless we don't have any other option. Yeah. So these are just a few examples. I probably can skip them about matrix operations with numerical examples. So the multiplication of 2 matrices is A multiplied by B, and this is how we do it. I think you should have already made nested loops where you sum the elements at the index I and G to calculate the multiplication of 2 matrices. But now you can just call np dot mat multiplication A and B. So it's going to execute this operation. Okay, A11 B11 plus A12 B29. You know the index must match between the K here, okay, the G here and the I here. Okay. So this is pretty much simple. We can also use the at operator, okay, and you should not confuse dot product with matrix multiplication. They are 2 different things. Okay, so this operator is for matrix multiplication. You can also use the at, but the dot product is something different. It's not the sum of the products, it's just the product element-wise. Okay, look at here. Okay, this is the numerical example. It's the sum of products element-wise, and here it's only the product element-wise. So you should not confuse. This is not a multiplication. So we use this operator, the dot operator, with a circle to represent the dot product, and here we use NP. So we can use the star or NP dot. NP dot like we used here in the dot product here. So we can use the dot product using NP dot, or you can use the star operator in Python. Okay? Yeah, the star operator, it will make element-wise multiplication, which is equivalent to the dot product. So
We want the sum of products. What should we do?
the sum of product is this one, mat mul, or the add operator. Okay? So the star operator here is for dot product. It's not multiplication. It's element-wise multiplication. This is not element-wise multiplication. The product of two matrices is a new matrix where each element is computed as the dot product of rows. This is a dot product, and this is a dot product. The dot product of the rows, not element-wise multiplication. Yes. Okay? It's simple. These are linear algebra concepts mapped to NumPy arrays. So there are special matrices in linear algebra which have their equivalent notations in NumPy. The identity matrix, which it's a diagonal matrix with all values equal to 1 on the diagonal, and elsewhere it's 0. And you can create the identity matrix using np.I, and you specify the number of elements of the diagonal. Okay? So in this case, it's going to create a 4 by 4 matrix with all the diagonal equal to 1 and other values equal to 0. This is what we call the identity matrix. And if you multiply any matrix by the identity matrix, it's going to result into the same matrix. A diagonal matrix is more general. So all the values except the diagonal are zeros, and the diagonal will take values like D1, D2, and so the identity is one special case where all the Di are equal to 1, but they can be other values. Okay, np.diagonal, you can provide a list to the constructor, and it's going to construct, so all these value will be for the diagonal, and every other value will be just equal to 0. And you can call np.diag, so this is going to return only the diagonal elements.